Hello, Linear Algebra student. This video is for Chapter 3.2, Part 2. Continue with discussion of the theorems related to determinant of a square matrix and how they relate to elementary row operation and other stuff. So we have two theorems that we introduce here. Theorem 3 is elementary row operations. If you do elementary row operation, you can actually figure out the determinants. Another one is if it is a square matrix and it is invertible, then the determinant is not zero, and it would expand our inverse matrix theorem. So you can see that knowing the determinant of a matrix is very important, or vice versa. So if it is not zero, we know it's invertible. If it's invertible, we know it's zero. It's actually um, um, and you can see that rows and columns dependencies actually affect the determinant. So if the columns are dependent, then it's not invertible. That means the determinant is zero, or the other way around. Now, with all the things that we know about how to calculate determinants and its relationship with elementary row operation, now we have two tools in our hands that we can use to calculate uh, uh, determinant of a matrix without a calculator. So for example, I have this matrix and I want to use cofactor expansion as well as elementary row operation to find the determinant. So kind of like to find the determinant in the least steps. Okay, so the first thing we look for is zeros or in a row or column, right? So that we see a zero in this, you can say this row or this column. I would, oh, it's blocking it. I would say I'm looking at it as a column because when we do row operation, we usually clear zeros in a column. So it would be nice if I can clear another zero in this columns, then I can expand on this column. So the target would be to clear this zero because I have a 1 here. So I think I'm going to do the determinant of A would equal to the determinant of getting rid of a 0 by elementary row operation of what? -3, -10, -7 of doing row 1 times 3 plus row 3 put back to row 3. And because I don't change anything, so it's the same as this new matrix. So -3, -9, -6. Oh no, 3, 9, 6, and then -3, -10, -7. I will become 1, 3, 2. Second row, I don't need to do anything. And then it will be 0, -1, -1. Now, if I am to complete the whole thing, I'll do this, but I'm not going to. I could just do the cofactor expansion. So this would equal to, the determinant of this would be equal to 1 times the 2 by 2 matrix, determinant 1, 2, -1, -1. And that is 1 times AD minus BC, right? -1 plus 2. That is equal to 1. Do I have 1 here? 1, 3, 2. Yeah, it's equal to 1. So I use calculator to check that it's equal to 1. You can see, you can combine them together because for cofactor expansion, if you are going into a 2 by 2, it's very fast. So this one also, so I have, so earlier I have a column 1, right? Expand above column 1. I can actually expand anything. I can expand column 3. So I have a 0 here. I'm not going to expand the row because for elementary row operation don't let me like switch rows around, but I can switch this. So I can see that I can get rid of, which one should I get rid of? I can get rid of this, the third one, right? Or the second one. What do I want to do? I want to use this because this is a smaller one. So the one that you want to get rid of is the one that you don't multiply it. So I would say determinant of A would equal to -1, 2, 0, 11, 4, 6. Just copy it over first. And I want to get rid of, I don't want to multiply this is the one that I want to get rid of then, right? So I would say -2 of row 3. If I multiply it, I cannot get rid of it. So I would multiply another row to get rid of the row that I don't multiply. So just keep track of which one you're doing. So it'll be -8, -6, -6. I'm going to add to 11, 4, 6, and that is row 2. So you go to determinant of kind of, sorry. This, you go to the determinant of 1 is the same. The second one is what I use. So you see I use row 3, so I don't change row 3, right? 4, 3, 3. But I replace row 2 by 3, -2, 0. Right? So now I have 2, 0, and this is the only one that is there. So I'm going to just do row expansion. I could make it an upper triangular or lower triangular by doing this, but I'm going to just do expansion. So expand out of 3, which is plus, minus, plus, minus, plus. So it's 3 times the determinant of -1, 2, the cofactor, 3, -2 of the submatrix. So that is 3 times 2 minus 6. So that is -4. 3 times -4 is equal to -12. Okay, equal to -12. So that's like find the determinant by elementary row operation to clear some elements in the row in the column, and then just expand out of that. And because of that, because of the inverse matrix theorem, we can also use it to check if vectors are linear independence now. So in the past, we would have to use, solve it, look at if it has trivial solution for the homogeneous solution, all those things. But now we can use the determinant. So we'll set a vector called 7, -4, -6, -8, 5, 7, 7, 0, -5, and we want to find the determinant of it, right? So what is the determinant of A? Now, can I use a elementary row operation? It's not easy. Can I factor anything? It's also not easy. So this is something that we might need to stuck with cofactor expansion if we're doing it by hand, right? So we have 1, 0 here. We'll expand 7 and -5. So that would equal to 7 times delete this row in this column, -4, 5, -6, 7, plus okay, so plus minus plus minus plus, so -5 of delete this row in this column is 7, 7, -8, delete this 2, -4, 5, right? So it'll be 7 times -28 plus 30 minus 5, 35 minus 32. So that is equal to 2 times 7, 14, minus 5 times 3. So 14 minus 15, that is equal to -1. Yeah, so this is the determinant. So are they linear independent? Yes, because it's not 0. So this determinant of A is not 0. So we can conclude that the columns are independent because it's invertible according to IMT. So this is the usefulness of it. You can use it to see if vectors are independence. Number 5, A is theorem 5 and 6. Two more theorem is the A transpose and A itself. The determinant is the same, so it can be proof as a result of cofactor expansion, because if you rewrite your row as a column and you expand around the column, it's actually basically the same expansion. So that is the proof. Theorem 6 is, this one is very useful in proving a lot of stuff. If you have a determinant of a product of a matrix, of two matrices, that is the determinant multiplied together. And remember, it doesn't apply to sum. Okay, and how to prove it? We prove it by the fact that if they are invertible, they can be written as a sum of elementary operations. So A is from IN to E1, E2, E3, all of them are elementary operation. And so if you multiply them together, you basically are multiplying all the elementary and all the I together, and you can redistribute them to the same things of which is the same as the determinants of A and B. It's the same E and I multiplied together. So that's the idea of proving it. So just remember that. And because of that, we can also use it to find what is the determinant of A power. So if I have A equal to this, what is the determinant of A to the cube? So we say determinant of A times A times A is determinant of, so basically it would just be determinant of A 3 times, right? Because according to the determinant A times B, it's just A and A is together. So what is this determinant? So we say determinant of A. I think I did it with the calculator, 3, 3, negative 4. So let me see if I have it. 3, 3, where is it? 3, 3, negative 4 is over here. So C is 24. 3, negative 2, negative, yeah, it's equal to 24 by the calculator. If you had to do it, you can factor. I think you can factor this out. Oh, I think we did it earlier. So you can factor this out and then do some elementary row operation. You can do it. So it's 24. So determinant of A cube would be 24 to the cube, which is equal to 13824. Last one, explain why determinant of K times A equal to A to the power n determinant of A. So a scalar is K, right? So if I want to do KA, that means every single entry has to have AIJ, right? AIJ times K. And this is only possible if you do this, K, do it like an identity matrix, but K in the diagonal times A, right? You do that, then every entry would have K in it, because just imagine if you do row and a whole column, so only the first one is multiplied by K, and another row and the column, so only the first one is multiplied by K, and you get the idea. So this is actually KA, right? So what is the so this is actually equivalent to K times A. So if I want to find a determinant, so that would be the determinant of this K matrix, Ki matrix, N matrix times A, right? And by theorem, is it 5 or 6? By theorem 6, I have two matrix multiplication. That would be determinant of the Kn matrix times determinant of A. And determinant of K is just a diagonal matrix. It's k to the n, right? The determinant of anything that is upper triangular or lower triangular is just the diagonal. So it's k to the n times determinant of A. So all of these properties that we've seen actually can be proven by any of these. Theorem 6, AB equal to AB. Transpose is the same. And also, yeah, so this is adding on to the IMT and theorem 3. Okay, so that's the end of 3.2.